Nice. So welcome everyone to this week's Intercontinental seminar on gravity and cosmology. This week we have the pleasure to have with us Laur Järv from University of Tartu in Estonia. Laur got his PhD in Durham, and after spending some years in Germany, in Vienna, he's been in Tartu ever since. And today he's going to talk about global portraits of inflation. So, Laur, the floor is yours.
Thank you, Kostas, for a nice introduction, and thank you for inviting me. I'm glad that so many people have attended. I'll try to talk about a series of works up here on the topic. So it all started several years back when we tried to write a dynamical system for the whole history of the universe, from inflation to dark energy. Unfortunately, it was peak COVID time, and there were some little mishaps in making the plots, so we didn't fully understand the full range of problems involved. And the remaining, the following papers were just trying to understand one part of the problems which we encountered there, namely concerning inflation. It turns out that there are not so many works yet on writing a dynamical systems formulation or phase portrait description of inflation, while there are so many about dark energy. So it was my intention to clarify it for myself, and maybe my talk now is to share these insights and invite you all to look more closely on the nice features of inflation in the phase portrait description. So yes, so we with these dear colleagues, I was able to advance the topic, and the final state now is we have non-singular variables which work for all states in the phase space. So my talk, I tried to be not too technical, because the equations can easily fill the whole screen if we try out different variables. I just want to give some introduction to nonminimal coupled scalar field in metric and Palatini formalisms, because they can be treated in parallel in the same way here. Some recap of early universe low role, inflation, and how it is described in the phase space, and then the quest for optimal variables. And the final product will be then, the final approach will be then shown in certain examples. The examples are chosen so that they predict the same spectrum of perturbations. They were before the Atacama results earlier in, I think, March or April this year. So they are still metric Higgs and Starobinsky and so on. But I'll come to these examples. First, we start with the scalar tensor gravity, non-minimal coupled scalar field in so-called Jordan frame. And we can treat both metric and Palatini formalisms. So Palatini formalism means that connection is not given just by Christoffel symbols of the metric, but is independent. However, computing varying the action with respect to the connection gives an equation which relates this connection to some other metric conformally related to the original metric. And in the end, after some maths, the equations in metric and Palatini formalism can be written in the same form, just using these symbols, delta m and delta p, switching in metric or Palatini terms. So here is the metric equation, and here is below is the scalar field equation. We see just if we are in Palatini, some terms turn on, or in And in metric, maybe these terms then turn off, so slightly modified dynamics. But if we inspect it closely, then Palatini and metric models are related by a simple transformation, namely this kinetic function is just modified by this contribution from the non-minimal coupling function. So in a nutshell, in scalar tensor gravity, Palatini models are equivalent to metric models after this transformation. So they are not a totally new class, different from, let's say, f of r. The Palatini f of r and metric f of r are rather different theories. So we do cosmology. We just take flat, spatially flat, cosmology, very simple. Then the equations again are similar in the Palatini and metric cases. We neglect the matter fields in here because in inflation, universe expands so fast that all the matter fields are diluted and only the scalar field remains. So the matter fields don't play much role during the main part of at least slow roll inflation, while they, of course, will be important when we connect to later stages of the universe through reheating and so on. For later, I have to introduce this W effective barotropic index. Formally, it measures the rate of expansion. Okay. And I also draw attention to the fact that this first Friedmann equation relates Hubble function H and the scalar field phi, so that of the three quantities which are here in the equations, only two are independent. It's important to then study the phase portraits. They are all planar, very nice to depict. Now scalar field, slow roll inflation. We know that inflation must generate nearly scale invariant spectral perturbations. And there are other problems it must also solve. So we need accelerated expansion, which means that W effective is less than minus 1/3. And we must generate a lot of expansion so that at least from some point during inflation to the end of inflation, the scale factors has increased by e to power of 50 or 60 times. So by this 50, 60, it is that time the perturbations that now characterize CMB, cosmic microwave background, and also cosmic structure of galaxies and so on. They were generated in a causally connected patch, and then the universe expanded, and we see the spectrum is the same from all directions up to small perturbations. So this is a model here. We have some potential for the scalar field. The scalar field is going down this potential. Here is the time, this CMB time, when the perturbations which we see today in the sky are generated, and here is the end of inflation. And during that time, the universe had to expand a lot. And when the field gets down to the minimum, the potential reheating starts, and there are another mechanism like some quantum resonances and so on, which can generate reheating. So how to get this accelerated expansion? It happens during slow roll regime, where the kinetic derivatives of the scalar field can be mostly neglected. So we effectively have just like de Sitter space, the value of the potential is generating constant H, and only small, let's say, deviation from that, so that we are nearly de Sitter regime. And for the scalar field equation, again, this field is slowly rolling. The phi dot is so small that the phi dot squared can be dropped, and as well as the phi double dot, they are very small terms. So how to realize this regime? It's either having very flat potential or very strong friction. So this term here can be interpreted as a friction term. Universe wants to, I mean, the scalar field wants to roll, but it is slowed down by this typical friction. If you think of this equation as a kind of mechanical analog, then the friction is usually proportional to velocity. So here we can also realize this situation, although the slope is kind of already a bit steep, but we have friction and we can have accelerated expansion nevertheless. So what is important for inflation is that this slow roll and this expansion must end. So there is a graceful exit. We cannot, I mean, there is no point to have infinite duration of this expansion. We would not be there to observe it. We observe a universe which was expanding fast in the past, but not now. So there must have been graceful exit, and it's not so easy. And this also explains why the treatment of inflation in terms of, let's say, dynamical systems and phase portrays is a bit different from dark energy. Of course, for dark energy, we don't know whether it remains or not, but at least it is like our future and universe might stay there. For inflation, we know it cannot. And now the question is, if you have this regime, if some terms are sometimes small in the equations, how common it is among the solutions in a given model. Like if we change our initial conditions a little bit, give the scalar field a little more kick here, would the same regime stay, or would the scalar field quickly, run down and we won't have our long inflation? So this is a question, how to understand, how to check this robustness of choosing initial conditions. Second issue is inflationary observables. Namely, we can measure the spectrum of perturbations in CMB and in the cosmic structures. For a long time, it was Planck, I think 2018, but this spring we have new results coming from Atacama Cosmology Telescope. The old Planck sweet area for the scalar, this NS and tensor to scalar ratio R as measured. It was here, this orange blob, but now with the new results from this ACT, the main area has shifted a little bit towards higher NS. I'm just mentioning for you to realize that there is some difference from the usual wisdom, but it's nevertheless a great result that we can already constrain many of the models, namely minimally coupled, just let's say quadratic and quartic potentials. They are ruled out. They predict much higher tensor to scalar ratio, and they are ruled out. And we can constrain the range of models very well. So how to compute? Is there some easy way how to compute the spectrum of perturbations? Indeed, there is. What we have found in the past that there are some quantities which are invariant on the conformal rescaling of the metric and reparameterization of the scalar field. These are symmetries of the original action without matter. And we can reduce all models to so-called invariant field and potential. We take the original model functions A, B, and V, and the scalar field, and in the end, write this invariant potential. And from this invariant potential, in terms of this invariant field, it is easy to compute inflationary observables. It is kind of shortcut to Einstein frame, a quick way how to compute. So there is not much need to do everything from scratch. If you have some model with this in this class of theories, then you can easily compute. But here it is also clear that there are many models with different model functions that predict the same values for the observers, because the resulting invariant potential is the same. So a natural question arises, is the dynamics of these models all the same, like everywhere, or maybe only in certain parts? And this is another motivation why to study these global phase portraits. Okay, now I go to some key features of scalar field cosmological dynamics. I take some old classic papers and just study minimally coupled quadratic potential, like some might call it chaotic inflation. So already back now, how many? 40 years. There were already key insights, basically understanding the main feature depicted here on this diagram. So the authors took X as a scalar, dimensionless scalar field, and Y as the derivative of the scalar field, also made suitably dimensionless, dimensionless time as well. And then they plot this scalar field on the horizontal and its derivative on the vertical axis. And all the solutions give the following diagram as here. So it's already a phase portrait. And it turns out that there are some solutions, these kind of horizontal ones, which draw all the other trajectories close to them. So a little bit of more closer inspections shows that there is a kinetic regime where the phi dot dominates over the potential. It's here and down here. And then there is inflationary regime where the derivative is very small. So we're very close to phi dot being 0, but not exactly. So this is this horizontal trajectory, horizontal solution. And finally, in the very end, there is oscillatory regime where scalar field basically oscillates around around the minimum of the potential. So these three regimes were noted also that this kind of trajectory draws other trajectories to its fold. And furthermore, they also compute the global phase portrait. So there's a nice trick called Poincaré map or Poincaré transformation, where an infinite plane, as here, can be mapped to a unit disk, as down here. So the radius outer rim of this disk is just infinity, and all the points within infinity are mapped into this circle here. And in this way, it turns out that all these trajectories which start here, at least when mapped to a unit disk, start at the same point. They call it K. And the other point, this other trajectory, which is here, then going to the, continuing to infinite values of scalar field, we start at some other point, which in the dynamical systems terminology is called a saddle point. Saddle means that on both sides we go into it and there is only one trajectory out. If this were not infinity, there would be another trajectory out, but that is already non-physical or not allowed mathematically, because this circle is infinity. So there is a saddle point, and saddle points they have this feature that only one trajectory goes out and other trajectories come closer to it. They call it separatrix because it separates this from S to F, or S1 or S2 from F. They separate two parts of the phase diagram. Now, the same plot was generated also now more than 20 years ago. I remember at that time, Lev Kaufman was giving some summer school talk and explained that you should really pay attention to phase portraits because they explain everything about dynamics. And the whole dynamics is encoded here. So in this plot from the paper, they also plot H, the Hubble function. So there are two surfaces. Upper one is expanding universes, positive H. Lower one is contracting universes, negative H. And what we see here on this plot is exactly the same. So there are R, there is this, the one which is a repeller. All trajectories start from it. They are like, our dynamics is repelled from this point. It's the kinetic regime. We start from kinetic regime, and then there is this red trajectory, which is inflationary regime, running from the saddle point to the minimum of the potential, and oscillating here. Going around means oscillating. So basically, going around means that the scalar field is oscillating between positive, negative values, and its derivative. I mean, this is rate of change of the scalar field is small because we are close to small phi dot. Yeah, and this encodes everything. A little problem with this choice of variables is that it very nicely gives all idea of what is going on, but the equations themselves become infinite in the asymptotics. So if you write the equations in terms of these variables, at the asymptotics where phi goes to infinity, phi dot also goes to infinity, and H also goes to infinity. So we are not really able to analyze the points themselves. We see them on the plots, but we are not able to analyze them, analytically very well, at least. So some other variables would be better. And I jumped a few years further. Some other kind colleagues have considered other types of variables, different variables. For example, this Alho and Ugla. Now, 11 years ago, they take the same model, but they a little bit modify the variables. We can take any combination of phi dot, and H, and establish two variables here, and have them face space and face portrait. We see the qualitatively, yes, the phase space is now a cylinder, kind of cylinder here, but the same points, the same types of points are represented, and the same three basic behaviors are also visible. So there's M, which before was K or R, repeller kinetic regime, where all other trajectories start to every direction. The solutions go out from here. Then there are these de Sitter points, which are saddles. Trajectories, two trajectories come in, these asymptotic ones, and one goes out. And other trajectories always come closer to it. They start from here, but they come closer to this separatix. And then finally, oscillatory regime is not represented by a point, but this kind of circle going around. And the benefit of this visualization is that here we can, here the asymptotic points are now regular. And I think Alho and Ugla also, they are very mathematically minded. They also use a nice technical term called heteroclinic orbit. So heteroclinic orbit is basically a trajectory which starts from one fixed point here, let's say de Sitter, and goes to another fixed point. Now it's not very nicely seen as a fixed point, but it's a kind of circle. But anyway, heteroclinic orbit from one fixed point to another. There are also, in principle, in dynamical systems terminology, there are homoclinic orbits which start from one fixed point and return back to it. So don't be afraid of this term heteroclinic orbit. Rather, it is the key feature of inflation, because at the Sitter we have accelerated expansion. This accelerated expansion more or less continues along this particular orbit. Other trajectories come close to it, so we have the nice feature that we always start from this kinetic regime, but into different directions at different speeds, we always end up near this trajectory, so that inflation is practically guaranteed to happen for all solutions. Exception is those that somehow are so lazy to come close to this separatrix or heteroclinic orbit. They only come close to it in the final oscillating phase. But there are lots of large class of trajectories that start in the kinetic regime and come close to the slow roll attractor trajectory. Another interesting choice of variables is here by Hrychna. He is basically inverting the picture so that asymptotics is mapped into the center. And it allows him to study this original de Sitter state because it's mapped to origin and it's finite. We see that still there are these, it's a saddle, there are trajectories that come into this R, and then only one goes out, and this one that goes out is attracting other trajectories. The actual model he studied is a little bit different from the minimally coupled quadratic, but we see the idea. So there are many models which basically really reveal the same types of behaviors, and now the question is which one is the optimal. And I have tried to construct and to reason, at least for myself, what could be the optimal way to depict. Here are my arguments. First, I want variables to work, the same variables to work for all model functions, so that we can compare different models. It is very common especially in studying the late dark energy, to take a combination where one variable is related to the square root of the potential divided by h. It makes a lot of sense because here we have like a variable which captures the potential energy of the system, and the other variable would be phi dot over h, which captures the kinetic energy of the system. And adding them up, let's say this one squared plus that one squared gives nicely 1. So it's like energy conservation motivated. But if we take one variable to be v over h, we might not be able to close the system for arbitrary potentials. Only nice potentials like exponential allow us to use it. However, if you take phi as one of the variables, then we can express all quantities which appear in our equations, like a of phi or a prime of phi, and so on. In terms of phi, we have no issue that we have to somehow replace a of phi in terms of v, and may generate some extra quantities to close the system. So I argue that phi is a nice variable to take to compare all kinds of models. Other particular choices might be good for some particular types of classes, but just taking phi is good for all. Then the diagram should be easy to interpret. So it would be nice to map scalar field infinity to the outer rim of the compact diagram, not to the inside, because well, it would be easier to read. From minus infinity maps to -1 and plus infinity to +1, not vice versa. So just taking a look at the diagram should give already kind of clear idea of what is going on. And now another crucial thing is to render the system regular in both asymptotics and the final state. In the asymptotics, where we have scalar field derivative and the potential all going to infinity. Well, there the naive combination phi and phi dot, the equations become singular, but also we have the same effect that the different asymptotic states are mapped to the same point, so we cannot distinguish them on the diagram. That's a kind of downside. However, it happens that this phi and phi dot over h is regular choice for the asymptotics. Equations are regular in this combination, and they also represent different asymptotic states as different points, which is nice. However, if we ask that the system is regular also in the final state, then phi dot is obviously regular, but this choice where phi dot over h is one of the variables, it becomes singular, because if h goes to 0, this ratio can also blow up, and we lose kind of predictability there. We cannot study analytically points which correspond to h equals 0, or like say v equals 0. So phi dot goes to 0 and h goes to 0, we have to be very careful what is happening. So this is also problematic. Therefore, combining all these requirements and making some trial and error and drawing some example plots for different choices, here is what we found. I'm going to skip all these technical details because it's a little bit boring maybe, and also the systems of equations, they get very long and cumbersome, and nobody wants to look at them. However, computers are still totally fine to compute and draw the plots. So here is my choice of variables. So locally, I have scalar field made dimensionless by the dimension full parameter m, which I assume to be positive. It can be Planck mass, but can be something else depending on the model. It's just rescaling the scalar field. And then I introduce z variable, which is phi dot over h for regions where h is larger than m, or phi dot over m. Basically, it's just phi dot where h is negligible. So in this way, we can mitigate the problems that phi and phi dot worked for close to final state, but not for asymptotic states, while the phi dot over h was conversely good for asymptotics and bad for the final state. So this combination, they make sure that the second variable is regular for both regimes. And finally, the best results are when we also little bit rescale adjust the time. So we measure time in this kind of expansion variables for large h, or just cosmic time t, where h is very small compared to m. And these are the good local variables which make sure that the equations are regular everywhere. And finally, we want to make a global diagram map infinity to a unit disk, to a unit circle, and everything is in the disk. So here is the Poincare map rule. So we have this subscript P for this Poincare mapping. And there is a minor detail S, which is just kind of rescaling variable. It is not introducing any scale. It is just showing if we have phi and phi dot, what is the proportion. Sometimes phi dot gets, when we get close to phi goes to 0 and phi dot goes to 0, let's say phi dot goes to 0 much faster, there we can adjust with giving S different values, we can visualize it better. And here is the final then result for non-minimal Higgs metric Higgs model, satisfying all these requirements. I'm again skipping the equations. Here I take some typical values for the non-minimal coupling parameter xi. Lambda is like in standard model, and S is just adjusted suitably, taking S, giving S different values. Oops, I mean, this central part will look a little bit different, squashed or elongated, but obviously the best way to visualize is if this final trajectories are like circles, going like circles. So, okay, this is my color coding. Of course, I have trajectories. I have the same points, fixed points. And I have different regions according to how they expand and accelerate. So we have super acceleration, dark green. This is going faster than exponential. It is possible in non-minimally coupled scalar field models. Then we have accelerating. There is light green. The boundary here, of course, is then W effective equals 1, corresponds to the sitter state. And we see that this point, which looks like a saddle, is exactly sitting at the sitter regime. Then we have deceleration, white, and also another interesting regime called super stiff. W effective is greater than 1, is yellow. And we have fixed points. Yeah, we have the final attractor, where all the trajectories end up. This corresponds to the minimum of the potential. Then we have saddle, C here, already noted by earlier papers, but now we can really analyze it in a finite way and compute that really the W effective is -1 and it is a saddle point. Then we have repeller and saddle. These are the kinetic regimes. In the case of minimal coupling, they were, and earlier plots, they were depicted as joined together, but really, if you see the W effective value, they are different states. They correspond, depending on the non-minimal coupling parameter xi, they correspond to different expansion regimes. D is repeller, means all trajectories go out, while E is a saddle, so there is only one asymptotic trajectory going in and one going out, otherwise they just get close to E. And finally, there is a gray region. It is non-physical. It is basically saying that there are no solutions which would satisfy the Friedman constraint. So we would have imaginary H here, or complex H, complex expansion. So they are not physical. It is artifact of these variables that we, in the span of these variables, there are some regions which don't correspond physically to real universes, which is okay. We just have to be aware that we don't look what is going on here, because it's just a mathematical artifact. Yeah, so we have these fixed points and regions, and now we can also see this separating, so heteroclinic orbit from the sitter saddle points to the final state, and we need that it starts at the sitter, although we must be maybe making some notes that it is not really the usual de sitter, because it doesn't correspond to h dot 0 or constant value of h. So h is changing, phi and phi dot are both changing, but in such a manner that this W effective is -1. And this is all that you need to have slow roll and accelerated expansion. Yes, we have this slow roll, as I said. Indeed, on this line, the slow roll conditions are more or less satisfied. There's a long period of acceleration, because let's say from D coming close to this orange line, it takes scalar field not so much time. But once scalar field is close to this orange line, in the slow roll regime, it is rolling slowly, and it takes a long time here. So it's a long period of acceleration. There is exit. It exits into the decelerated area. So the accelerated expansion ends as needed for inflation. And this slow roll is then also approximated by the slow roll approximation. If you remember some slides before, I had some terms in the equations made light gray, like fading away. This is the slow roll approximation. If we want to plot it on this diagram, this is the result we get. This is also another interesting topic, how to make it more precise. There are ways how to come closer and closer to the real trajectory by a series of adding more steps in the approximation. But the overall knowledge or overall result is also that the slow roll, naive slow roll, the first order slow roll predicts a little bit different point of exit from inflation than the real one. So they are quite a bit different in the value of phi. And this might be relevant, and there are papers on that also. And yeah, and this trajectory nicely attracts other solutions close to it, so clearly describes inflation, and everything is covered on this plot in a regular manner, and we can compute all in a regular manner in these variables. Now, this is for X inflation. What about other examples? Can we do it for other models? And indeed we can. We can take Starobinsky inflation given by this Lagrangian, but it's well known that it can be written in the scalar tensor form by introducing a scalar field like this. And we can then convert Starobinsky model into the same basic type or family of scalar tensor models, like here with a specific potential. Vanishing kinetic term doesn't mean that the scalar field is non-dynamical. No, it is still carrying dynamics because of non-minimal coupling. We can choose some. I mean, in this plot, we have taken the parameter beta to have such a value that we get exactly the same spectrum of perturbation, the same NS and the same R as in the metric Higgs case. So it's just in order to see what is same and what is different if we compare the global phase portraits. So what we see here is, again, of course, heteroclinic orbit. Now we have this gray is ruled out because this part would mean phi negative, would mean anti-gravity, so it's ruled out. And there is also this part which is ruled out is not happening. So there is only one de Sitter point, and we start rolling from here. There is a nice heteroclinic orbit from C to A, from de Sitter saddle point to final attractor point. It is approximated by slow roll, attracts other solutions, and indeed describes inflation. This inflation takes place on this patch here, and then we exit into the white area, into decelerated expansion, and then finally just keep oscillating around A. But there are some other solutions, which don't start from this kinetic regime. They start from some kind of singular state here at phi equals 0. But nevertheless, we see the flow that they come and approach the attractor, this master trajectory of inflation. And if they are lucky enough, they have enough inflation too. And people have studied initial conditions and found that indeed it's possible. It's all consistent. So, but the main point is, if we compare this diagram with the previous diagram, we see that the overall features, some overall features are the same, but the diagrams look different. So it's an answer that even when we have the same predictions for inflationary observables, the perturbations, the overall dynamics behind is qualitatively different, but some similar features. Now, here is a pole inflation model. Pole means that there are some values where the kinetic term becomes singular. And for simplicity, we have taken it minimally coupled. It is artificially constructed a bit to give the same spectrum of perturbations as the models before. So numerically the same exactly. Now the pole appears at this point B in the at some finite value of phi, where here we have 0 in the denominator. This point again, this B point is de Sitter at the pole. Inflation occurs where we flow towards small phi. We go from here or to here. But the field will not settle at phi equals 0 because by construction we have, in order to match the perturbations generated along this trajectory, we had to put phi squared here. And so this kinetic term vanishes at the origin. It is not a realistic model because we have a singularity now a singularity which is not due to the variables, but really kind of truly happening in the model. And so the oscillations around here are like super fast because the field is kind of, if you think of it as an analog of some mechanical model, it is massless. And furthermore, there is another heteroclinic orbit from these other points C to B, but there is no exit from inflation. So we just go from C towards coming closer to B, and we never reach B because B is a fixed point, and inflation never ends because we are always in the accelerated expansion regime. So it's not a realistic model of inflation, but it is instructive to have all these features, this non-physicality depicted on the phase portrait. We don't need to. We can immediately see what is wrong with this model. That there is a kind of singularity here, and so on. In the beginning, I had also Palatini scalar tensor. We can also construct artificially some kind of model which is in the Palatini formalism and gives the same spectrum of perturbations as metric Higgs and Starobinsky models. Just the potential is a little bit complicated here. Again, we see that yes, we have heteroclinic orbit from C to A. Now it is a little bit contrived because it's very close to infinity, this starting point. And then we exit finally into the white area, into the deceleration. But the slow roll path takes place at very high values of phi. And what is more and curious, and maybe not many people have noticed it, that actually during these oscillations, there are periods of contraction. At the final state, we oscillate. And if you don't include any normal matter, which should be included because of reheating, but if you don't include it, then we would see some contraction phases around the final state, which may be also a bit unphysical, but hard to say definitively, because at these oscillations also matter should be created. But if we have some evidence that maybe early on there was a little phase of contraction during reheating, then gives credit to this model that it could make sense then. Okay, I have already spoke a lot, and now time to make summary and a little outlook. So we know that slow roll attractor solution is not a fixed point, but a specific solution described by a heteroclinic orbit or the separatics starting from a saddle. This gives inflation, and it exists because of a specific fixed point structure in the phase space. So it doesn't come out of the blue. It must have a starting point, which is a saddle, and the final point, which is a tractor. And to fully uncover this structure, we need to look at the global phase portrait, global because we want to see from infinity to the origin. Sometimes, or quite often, the starting point for this trajectory is residing at infinity, and that's why we need to look at the global phase portrait. Not local is not enough. And to draw and analyze these global portraits, we have we are proposing a suitable set of variables that work for all models of scalar tensor family. And we can directly compare different models. It would be nice to check whether it can be extended to beyond this family as well. I guess so. They are easy to interpret. Map scalar field infinity to outer rim of the compact diagram. And then the scalar field 0 is in the center. And render the system regular everywhere, including both the final and asymptotic states, which can be then clearly distinguished, because if they are not, if the system is, let's say, singular in the asymptotic, then many weird things can happen and we cannot handle it mathematically. But here with these variables, we can. So why you would be interested in it? Well, it's a useful tool. If you have some model and you want to know whether it is realistic, before then starting to calculate perturbations, maybe just draw the phase portrait to check whether the slow roll orbit actually exists. It is not automatically guaranteed. I just in this talk, I showed you plots where it exists, but in the literature I know also, I mean, in my work as well, that there are some cases where this slow roll orbit actually resides in the non-physical part of the phase space, so it doesn't exist. So it's a quick check. If you have a model, you want to test it, draw the portrait, see whether it makes sense. It has all these features which guarantee you nice evolution. And if it's the case, only then go and calculate the perturbations, because if you don't check, you might be calculating perturbations in the non-physical region and nothing makes sense then. So, of course, there are many things to do to understand, extend, and generalize. Study more models to get confidence that these variables really work and do their job as expected, but also study more theoretically fast roll, rapid roll, ultra slow roll, constant roll, otherwise non-slow roll scenarios, whether these, what are the features, characteristic features of these scenarios. Can we find something qualitatively? It would be maybe interesting to further understanding in this respect. Also extend it to non-minimal coupling, and then extend the non-minimal coupling to Gauss-Bonnet or other higher curvature corrections, other types of models, maybe teleparallel, maybe metric affine frameworks, lots of models around, and it would be nice to kind of see they are working in the same framework with the same variables, so that these plots can be just put next to each other and analyzed and commented and compared. Yeah, so I think for dark energy, there are like hundreds of papers. For inflation, there are, okay, more than 10, but let's say tens of papers, and there is a lot more work to do. I invite you to try it, and if you have some ideas, tell me and collaborate, and let's further the knowledge of early universe in this way. With this, I think I stop. Thank you for your attention. If there are any questions, I would be happy to try to answer.
Yeah, thank you very much, Laur, for the nice talk, and thank you for staying on time. Yeah, are there any questions from the audience?
May I ask one?
Yeah, go ahead, True.
Yeah, thank you, Laur. Thank you for the nice talk. We do actually have a model, and maybe I can send you an email later. But anyway, so before having, so I want to clarify something. So does your method work even for instance, the model with derivative couplings, or even for model with ghost?
I have so far tested it only for this particular family of theories here. So derivative couplings not present, but it would be very nice to try to check it. I think it does not introduce any new variables. It should be possible. I'm very curious how the portraits would look like.
I see. Yeah.
Yeah.
Because so usually when people talk about derivative couplings, then there are two different ways. The one, like assuming some specific coupling such that there's no higher derivative appearing, even there's a derivative couplings. But if you consider some couplings between, for example, Ricci scalar and energy momentum tensor of the inflatone, then you are going to have higher derivative couplings, and so if you just consider slow roll approximation, you can just argue that those derivative coupling, I mean higher derivative coupling do not contribute, and then you can easily do calculation the spectrum, the tensor to scale ratio, those observables. But yeah, I'm also curious about what happened in the dynamical portray there.
Yes, so maybe these higher derivative couplings, they are not important in certain regime, but in the whole dynamics, somewhere they play a role. And it would be nice to see what are they doing there.
I see.
Just, these global phase portraits, they are nice to draw when we have only two variables. I mean, two independent variables. If there are more, then we would have some, three-dimensional plots, which are more hard to understand. But of
like
course, it's
multi-field inflation, etc. Right?
Yeah.
Thank you.
Yeah. Any other questions?
Hello. I have. Sorry.
The phone question. You talked about so low inflation, but how you can see that this inflation is really so low using your face portraits?
Yeah, it's a good question. So we know that the saddle point is the sitter. It means that if we put the scalar field there, it is just sitting there. It is not going anywhere. A small deviation from it, this scalar field starts to roll. And initially it starts to roll very slowly. So in this way, we know that it is slow roll. And we can also plot this approximation, and we see that it is this approximation, slow roll approximation, kind of approximates the real trajectory.
Okay, but there are some models then using during inflation, they are not only so low phase, but also so low phase. And
yeah, ultra slow roll, yes.
Is
think
it possible to see some distinguish between such types of models using phase
exactly? I am very curious. I would like to see it, but I haven't checked. It was my the final point here that there are these ultra slow roll or constant roll or maybe non-slow roll models. What does it mean really, and how common is inflation in these other models? Here we see that for these models, slow roll, it's an attractor regime. We start in kinetic regime and come close to this slow roll regime. While for other models, I don't know whether there might be some regime which generates perturbations which are meaningful and match our observations, but maybe this regime is not an attractor itself. It's just a very specific solution or very transient or something. And to understand it, we need to draw global phase portraits.
Thank you.
So there are a lot of questions to ask further.
I think Lakshmi had a question.
Yeah. As you said, there are a lot of paper in studying the dark energy issue, and also there are individual paper studying in inflation. But do you think is there a way to, by considering this model, we see a very nice inflationary era? Just to extend this work, like can we see with the same model both inflation and dark energy?
Yeah, very good question. Actually, I see Chibitesh is also here in the audience. Reminds our paper 5 years ago where we exactly tried to model have a dynamical system description for the entire history from inflation to dark energy. And one of the stumbling blocks that we encountered that we didn't fully understand was inflation. Now, to make inflation to connect to the late history of the universe, one has to implement reheating. So inflation is relatively simple, although it has its own intricacies, but we need to then connect it with other fields. After inflation, all other matter which was present is diluted kind of away. Its density is basically zero, and we need to recreate it. And the question I mean, as an open question to everybody, how to express reheating in terms of dynamical systems. It must be some interaction between the scalar field and the other matter fields, how to do it in a nice way. And then if this is done, then we can connect from inflation to late universe in a very meaningful manner. But yeah, this extra process must be implemented. And we were hoping it was not necessary, but now I know that it's no way to really meaningfully connect. Right now we can study early or late separately.
Okay. So like it's a little bit difficult to interpret both of them, but it could be possible.
Yeah, I'm sure in someday it will be possible, yes. But it needs some work.
Okay, thank you.
Nice. Any other questions?
Hello, Laur.
Juvitas?
Good to see you after a long time, Laur. Now, I was just curious, you said no to check this low roll condition. Can we devise some quantitative criteria for when the slow roll heteroclonic orbit approximation is valid? Can we have some criteria like in mathematically?
I think the simple criterion is that we have the sitter point, which is a saddle. And then we know that from the sitter there is a trajectory out, and along this trajectory, slow roll is satisfied. However, of course, there are some mathematical subtleties. Saddle means that there are, let's say, linear approximation is valid. But to be very true, I think in most of these cases, the saddle-looking points are non-hyperbolic. Means that there is one eigenvalue which is zero, and so we need to go to the next order approximation, center manifold or something like that, to really check. But of course, the feature is like the sitter, so two trajectories going in and one going out.
Maybe.
And I think this feature guarantees that we have some slow roll somewhere.
Okay, thanks. Maybe you can find out in terms of eigenvalues if we can work out in terms of like center manifold and all. If we do some calculation, maybe we can quantitatively find some criteria.
Yeah, I mean, in our variables now, it is possible to actually compute eigenvalues for these asymptotic points. They are very cumbersome, of course, but it is possible.
Yes.
Before, if we had asymptotically the equations became singular, then it would have been much more troublesome.
Thanks.
Thank you.
Jayo, did you want to ask something?
Yeah, actually, I just want one more question. So I'm still a bit confused about what you mean by the regular and singular variables there. So for instance, in the early part of your slides, you showed that all portray diagrams proposed in the minimal model, and you showed that there's a mapping. Even I think the even previous one.
Mhm.
Yeah, this one. So you show that there's a mapping to bring the infinity to the finite disk circle as from figure A to B. So does figure B count as a regular variable set?
No, if we if we write our original equations in terms of these compact variables, then we see that they have a singularity.
Okay.
Yeah.
In terms of variables.
Yes, in terms of these, compact variables, we have a singularity still around this disk. We can plot them, but it's very hard to analyze what is going on in this point.
I see. Okay.
Because the system is kind of, divide by zero or infinity.
I see. Thank you.
Nice. Are there any other questions? I want to ask Laur, like, how feasible would it be to numerically explore the global portraits? Let's say you have potentials that are constrained from current CMB data. Do you think that it might be possible, like, to classify attractors across parameter space?
Yes, I think so. Yes, I mean, of course, all these portraits which I generated here, they come from quite long equations which can only be manipulated on computer, I would say. It's just half a page of equations and nobody wants to analyze it by hand.
Yeah.
But conceptually, it's kind of, to me, it's already kind of algorithm. I just put in A, B, and V, and I generate the plot.
I see. Good. Okay, let me stop the recording.